Like you want to have external volumes that have all of the persistent data, and then I can. That's getting me off the top of my head. That sounds like an easy idea to implement, but it also I can't figure out how I would implement that. So, hmm. All right, we are back, and now I ask that you imagine yourself in the shoes of a guy who maintains a Linux machine that's pretty old at this point. So you've had the same install on this computer since 5 years for incrementally upgrading since Fedora 32 or something along those lines. And you've customized things pretty heavily. You have your own custom greeter. You got non-standard network conditions in your house, so you've done some weird things with your network setup. And then you've got tons of your own scripts and a fully customized desktop. This is a very personal computer, and it's got data on it that you would be very sad to see go. It is very ephemeral, though, because if anything goes wrong, it's a lot of manual steps to get things back to the way that they were, and they never will get exactly the way that they were. It's also, since it is so old, very easy to accidentally trick yourself, shoot yourself in the foot by changing something small maybe 4 years ago, and then now that you're doing something relevant, things are acting in ways that you weren't expecting. And this sort of complicated data existing ephemerally and for a very long time in a way that gets changed a lot over time is very difficult to manage in a way that isn't host specific, or in a way that's actually transferable to other systems, or in a way that you can actually determine what data you care about versus what data you don't care about, because your system is a snowflake and you're never going to be able to make the same one again. So this gets you thinking, what if there was some way, some means of system configuration where you could concisely and declaratively encapsulate the state of your system that you actually cared about? If you could do that better than regular backups, what would that look like? Well, NixOS solves that problem, and NixOS was explicitly designed to solve that problem. On the NixOS website, it defines itself as reproducible, declarative, and reliable. Reproducible in that it is centrally configured from one location in the file system, and then from that configuration, which you compile, you get pretty much the exact same system state as what you defined in terms of the settings and programs enabled on your system. It is declarative, as aforementioned, it being derived from the Nix programming language, which will make your system be a result of logical derivations from your config file. And because of this, you can do things like, say, declare that OpenSSH is enabled, and then NixOS will manage all of the actual system state for you to get that result. And three, NixOS claims it is reliable. And packages cannot conflict because of the way they're built and the way that they're stored on the device. And past configurations, in case you messed up your current one, can be selected on boot. So this sounds like it's doing a pretty good job at solving that problem that we had as our theoretical Linux user with a weird system. We have something that sounds like it's perfect, even, almost. It's an operating system based on functional paradigms where you can explicitly define everything on your system. Oh, but you almost can, because there's still a thing called mutable state, and luckily there is something to be done about it. Title card, cold open, awesome. Well, first things first, getting things out of the way, definitions. What is state? State is the value of all variables and data within a system at any given moment. And I mean system in the general sense. A light switch has state. It's either on or it's off. And the initial state of a program, it contains all of the arguments that you give to it, your environment variables and other things that are pertinent to the actual program. There are also things such as stateful and stateless programs, and this is a much better definition in terms of what actually has to deal with state that may or may not change. Because a stateful program is going to store mutable data persistently, where a stateless program will not. A use case for stateful programs are things which will modify data that will be changed. So this is things like usage statistics, preferences that you set as your user graphically in a program, and anything that is going to not stay the same. And a stateless application is something like the GNU core utils, which will take input directly and explicitly and will give the same output every time, because the data that it retains is not existing, because it works with data that won't change over time. And a stateful program remembers things, a stateless program forgets things. That's an easy way to think about kind of categorizing those sorts of programs. And we kind of want to get rid of things that are stateful, or at least minimize the effect of statefulness on our system, because that makes it a lot easier to track what's actually going on. So stateful programs work with mutable state, and yes, Nix is to do with functional programming. But why do I say that we want to get rid of things that are stateful? Or what is the point to using a computer if not to change data? Well, let's look at an example with Git. Git can be configured imperatively in this sense with the git config command. When you set your username and your email using the git config -- global command, that is an example of stateful imperative configuration. Imperative programming is defined as using statements or commands to manually change the state of your system, system again being the general term, and it isn't very portable. If we want to use Git on a different system and we were limiting ourselves to using just these commands, then we would have to remember to run these two commands every time we wanted to use Git. Or we could do this through a script, but that seems a little bit weird to do. Before we go into the more portable way to configure Git, let's look at the imperative configuration of a system. Look in the same sort of vein as one program. Let's expand that to the entire Linux system. A lot of the time, you will see someone write a shell script to set up their local environment or their local system. You can do these things manually. It might be a lot of work to do all of this stuff manually, especially if you have a desired system state that is fairly complicated or fairly customized. But it makes sense sometimes in that case to have a script that does a lot of things for you, like pulling your dot files, elevating to root to set up certain system-wide configurations, etc. So as much as this seems like it makes sense, this is a pretty scary and a pretty weird way to configure an entire system. Because what could happen is, since we're not version locked on anything, if we move our script to another system that doesn't have the right version of software that we want, it's going to break. APIs change all the time, not so much in the Unix world, but especially if you're doing a bunch of sedoc nonsense, you have to be really careful about the output of the programs you're using. Also, we're not guaranteed to be using the same environment that the script was made for. We may have an environment variable set that is changing the behavior of a program that we're not expecting to behave in a different way. Also, if something fails partway through our installation, then we're stuck in a transient state. And that is very bad. We don't want that to be happening. So what is the alternative? I forgot this slide is in here. We're not going to talk about that yet. In computer science, there is the concept of side effects. In any mutated state outside of what's explicitly being done is a side effect. And so that's if we call a method and then some other variables are changed that aren't related to the result that we get from that method. This includes modifying a non-local variable that other things might read, or altering something that is passed by reference. Think about what happens every time you use your computer. You're going to have a bunch of different systems interact with each other. A bunch of different databases will update with everything that you do. Logs are going to get written down. And doing things imperatively with side effects is going to make it so that any given action you take on your device is practically, potentially irreversible. So that is just something to be thinking about, especially in the context of When you're making all sorts of different changes to a system, things have consequences, and so you want to make sure that you're getting exactly what you wanted. Some side effects are things that you are going to want, like in object-oriented program, when you call a method that makes a function, or sorry, makes an object perform a bunch of actions. I mean, that object is going to encapsulate its own state. And as global and as mutable and as weird as object-oriented programming is to a lot of people, it makes sense in certain situations to use object-oriented programming. And there are other side effects which are ambiguous or unexpected, which could change the execution of certain future things that you do, especially in ways that you aren't expecting, because the given input that you are providing isn't going to have changed. But if you did something different previously, that can still result in a different output. So in functional programming, this aims to minimize side effects. And it does this by using functions, at least in the definition of what a function is in math, or a pure function in programming, where the same input will always result in the same output no matter what you did beforehand. And this is done with as few or no side effects if you're doing a pure function. So the output will be deterministic based on just what you're saying in that one moment, and not based on what has happened in the past. Git can be configured declaratively. It doesn't rely on that imperative configuration by running the git config -- global commands. You have, in declarative programming, desired state that you decide, and then the program itself is responsible for actually meeting that state. So with Git, you can configure Git using a config file, and this is something that is portable, which doesn't rely on mutable state and does not have side effects. For example, when we're running git config -- global, we can't know whether that's going to write to .git config or .config/git/config. We can't know that without checking, and that's something which is dependent on the global state of our system. NixOS does things the declarative way through use of its Nix configuration, which is all essentially and deterministically evaluated. So we are actually going to be version locked. We are actually guaranteed to be using the intended environments for our scripts, and there is no transient state for us to fail in, with Nix particularly, because everything is built in the Nix store and then atomically linked when it is completed. Atomically meaning there is no interruption, there's no way to be in a weird in-between state. And it's immutable, which means that we don't have to worry about accidentally changing something or having something that we've declared behave differently based on something we've done before. Everything is generated, everything that is generated from our Nix configuration will be symlinked on runtime to the location that was immutably defined in the Nix store. And we have control over all of that. So that sounds perfect. Again, this is exactly what we're looking for. And we can throw it all out the window by just doing stateful things on NixOS anyway. So there's nothing stopping us from running imperative commands. There's nothing that is in place to stop our programs that we run from doing things imperatively. And there's nothing to make it so that we have to use NixOS and the Nix configuration files to configure all of our programs. We're not forced because Nix gives us an out, but what if we were forced to define everything through Nix? And what if we made imperative operation on our computer literally impossible to do? What if there was no disk for imperative state to be written to in the first place? And that's the idea behind impermanence. Some disclaimers, first of all, is that I'm not a Nix expert. I feel like I know about as much Nix as the average Nix user. So be prepared to lose data if you try this. Although also, it is the whole point. And then, just as a preface, this talk does assume that you're using Home Manager as a NixOS module through straight up plugged into your NixOS configuration so that you have everything in the central Nix store linked directly. We're not going to actually be talking about Home Manager, but for a full configuration of your entire system, including your user, you would want to be using Home Manager as a NixOS module in this particular instance. Also be aware that this is so completely overkill. I'm going to glaze it a little bit, but the regular person is going to be fine with regular Nix. All right, so let's talk again about our predicament, the problem that we're trying to solve. The programs we use are going to use global mutable state, whether we like it or not. And we, the users, only care about certain data that we explicitly are defining. Could we solve this by wiping the disk? A lot of stuff gets written directly into the Nix store, and that stuff is declarative. So if we just wipe everything else, does that solve our problem? Let's think about, let's actually walk through doing that. So wiping the disk, what's the easiest way to do that? Probably having no disk, actually. Let's just mount tempfs to root. NixOS can't boot without /boot and /nix, so those two are going to have to be mounted externally on like an actual file system. The easiest way to do this would be to use a file system that supports subvolumes, so Btrfs and ZFS would be good choices here to have boot and nix. /boot on Btrfs actually isn't the greatest idea, but you get the point. Pseudo file systems aren't going to be mounted by us. That's going to be handled automatically, so we don't have to worry about those. And now for the part that actually matters, is that we don't want to erase literally everything, so let's put data that we want to persist somewhere else, maybe in, I don't know, some sort of overlay file system that we can have in /persist. Okay, this makes sense. Here's the disk layout in NixOS to actually accomplish that. You would just have all of these as separate mount points that get mounted. So we have all the data that we care about now. All of it exists theoretically. How does it all link together? So remember 74 slides ago where I mentioned that NixOS can activate an arbitrary configuration on boot? I'm going to go back to that slide right here. There's two parts to the slide that actually are piquing our interest right now, and it's that NixOS deterministically acts to produce desired state, and past configurations can be selected on boot. All right, what happens when we select a configuration? Because that would start kicking into action all of the steps which we want to be taken. Well, so the bootloader entries for NixOS are stored in /boot/loader/entries, which is the most straightforward path on any Linux system ever on the planet. Thank you, systemd, for that. Since NixOS supports switching between vastly different configurations on boot, it needs to be able to tear down and rebuild the structure of the system of those directories which it has control over. And so once the configuration has been selected with the specific init script called from the Nix store, it's going to look through all of our directories that it manages, and it's going to check the state of those directories. It will even make them if they don't exist. So this is all handled by NixOS automatically on its own.
When you say at boot, this is still not in the bootloader. This is after it's loaded the kernel.
Yes, this is after the kernel has been loaded. This is before we have a usable system, but this is all happening as part of the initial RAM disk. Then NixOS is going to create the file system structure, and all NixOS knows is that the file system doesn't match the desired file system that we have in our config, so it'll create the symlinks and directories for us. And this is almost free to do, because NixOS would have to check all of the existing symlinks regardless, because as we said, NixOS can choose between arbitrary configurations on boot, so it has to know how to do this cleanup and rebuild. So, all right, we have the functioning bare bones element of our system, and this is actually something that fully works. If we didn't have the /persist directory, which as we do right now have it completely separately, not linked at all, this would be a system that works. We could use it if we wanted to, but we really don't want to right now because we have a Linux system which doesn't have any data at all or any way to store any of that data. We do have the skeleton of a system and all of the binaries of a system because all of that is linked to from the /nix directory, which is the Nix store, but all of the rest of the documents that we create and everything that we do on our system is going to disappear the instant we turn off our computer because we mounted root on tempfs. So there's pros and cons to doing this. We'll get to the actual way to store data in just a little bit, but there is a reason why you would want to have the data that you create be uncreated, a reason to have all this stuff wiped. For certain things, we want to be forced into doing them the right way. We don't want to use git config -- global. We want to use the actual git config file. And this can be managed through Home Manager on our NixOS config. That forces us to be explicit and forces us to be functional. Then also, as an added bonus with having our system wipe itself every time we boot, the system is going to forget about all of the software which we don't define, and it's going to forget about all of the garbage that may or may not be left behind when we experiment with things. So, for example, if you've ever used, I don't know why I'm blanking on it right now, KDE. KDE absolutely ravages your .config directory. It puts a ton of stuff in the root of .config, and it creates files all over your home directory. If you have an impermanent home, or if you just don't define KDE in your config, all of those files won't actually get committed to disk. You'll have a clean home directory. And you'll never have garbage floating around that you forgot about ever again. For other things, you will want our data to persist, however, because most things aren't config files. Your websites, cookies, your documents that you're writing, all of the Bluetooth connections on your system, all of the logs on your system. This is data we don't want to be erased. So how does that work? We want mutable state, as much as it hurts us to say, because sometimes the mutable state is our schoolwork. And so that's where the NixOS impermanence module comes in. That's an external module by Nix community. And we can define our own directory structure that Nix will, on boot, assemble from our /persist directory. So this is in NixOS, in the configuration language, how you would define for the impermanence module which directories you want to be persistent on disk. And this is managed via an overlay that exists on your whichever you defined as your /persist directory. All of these directories would be copied into there, and then all of the mutable data which you interact with is actually going to be happening entirely in this /persist directory, because all of these directories are going to be bind mounted. Oh, yeah.
Right there. So on the right, those are user directories that should persist.
Yes.
Okay. What about something like .mozilla, which contains your cookies, but also contains stateful information about your browser itself, like your extensions and their settings? Like, would you just also consider that to be persisted and not configured via configured, like your declarative syntax?
The one way to manage something like Mozilla, where you have stateful data alongside stateless data, is you could go through and manually pick out the files and the subdirectories of .mozilla that you want to be persisted, and then this would look a little bit more complicated. But another way of managing that would be just to use the Home Manager modules for Firefox and have that on persistent data regardless. Because, and that's actually the honestly much more sane way of doing that, because then you would have immutable state that's linked to the Nix store, and it just happens to live with the rest of your mutable data. Because as NixOS works on the regular way to use NixOS, that is what happens, is that you have the symlinks that are alongside all of your ordinarily mutable data. And again, as I mentioned, that works by having bind mounts, which is the same concept as a symlink, but it doesn't rely on the root structure of your file system remaining the same, which, I guess to recontextualize, you know how a symlink can have a relative path in the symlink itself, you can say this file actually points to a file which is in the parent directory or in a lower directory. Well, if we were to make symlinks directly to our /persist directory, this would work until we interact with something that's chrooted, because symlinks are based on our current root. And a lot of programs in NixOS rely on a chroot script or a chroot wrapper, and they have their own separated root. So these symlinks would point to different locations. And that's where the bind mounts actually become something necessary. Bind mounts are there, I just explained the same thing. The module will hook into the NixOS boot process, and then it will create all of these links and mount all of these locations before everything is written. And this just happens at the very end of our RAM disks setup process, which you can see right here. Whoops, not right here. I confused myself. And now, after everything is said and done, we've got the data that we don't want to be persisting itself wiped every time we completely reboot our system. And we've got the data that we actually cared about on its own separate file system on which only it lives. So we've successfully separated out all of the data in a way that we know, because we were the ones who came up with that, and we chose which directories go where. Do we have any questions right now? Amazing. Now let's get into some caveats. If it sounds amazing, I do apologize for deceiving you. There are several pros and cons to impermanence. Firstly, the pros. It keeps your system clean by default. If you create a bunch of garbage, or if you run, like for some reason you decide to compile a program from somewhere else, or if you download a bunch of scripts, everything's going to be gone by the next time you reboot. I like to use my desktop folder just for running a bunch of random scripts from the internet. Well, not literally, but it's my garbage stuff that goes in the sandbox directory. And through impermanence, that can be very easily, automatically non-existent. It'll force you to declare all the settings that you want to keep. This will be, in a way, stopping you from foot-gunning yourself 5 years in the future, because all the changes that you make to your system are going to be very concisely and very structurally defined by you in a central location. It lets you experiment with new software without cluttering up your system, and it makes your system a lot more portable, because you're not relying on the directories that may or may not be buried in between other directories that don't matter to store all of the state of your system. You're going to be writing it down explicitly, or storing only the directories which you actually have data worth transferring to a different computer, or worth making portable. And now here are the cons. Firstly, you're going to spend an unreasonable amount of time configuring your system compared to the benefit you'll actually derive from it. Your NixOS configuration will become overwhelmingly large if you rely on a purely impermanent everything. You will run into a program that doesn't have good Nix modules yet, and you will just have to say this program or this directory relies on the imperative state. You will get lazy, and you will add config files to your persistent data, or you actually might not, depending on how restricted you are, but you will think about doing this, and you will forget to add a program, then freshly log into it for 10 days in a row before finally deciding to do something about it. Then you will get comfortable, you'll install like Minecraft or something, and then you'll play for 3 hours before you realize that you didn't back up the directory that has your Minecraft saves on it, and then you'll lose everything. But you'll have fun. It may or may not be from experience. What's the question?
You said all the stuff that isn't persisted is on a temp FS, right?
That is one way to implement this.
How have you
I'm going to get to that in one slide. Here's the bonus slides. So, come on, where am I? Here we go. If root on tempfs sounds really sketchy, that's because it is. And so here's an alternative. Here, this is an example of in our next configuration, boot.initrd.postresume commands, this is what gets ran very last in initrd, which stands for the initial RAM disk. So this is a script which will start the moment our system turns on, right after everything else the RAM disk has taken care of gets taken care of. So this will, what this example shows is it will mount a temporary directory with which we can look into our Btrfs file system, and then it will move our previous Btrfs partition, or sorry, Btrfs subvolume, which was root. It will back up that old root and store it in a directory with a bunch of other old roots, and then it will create a brand new root, which is completely empty, and then the rest of the NixOS startup sequence will initiate, creating a brand new root with nothing on it. Now, just as a preface to this, we're not going to be able to use this isn't based on snapshotting, so this is going to use a lot more space than if this were somehow based around snapshotting, because this does rely on creating a brand new root every time the system turns on. So we will just have to eat the repetitive data being stored in our backup roots, because that gets created fresh every time instead of being derived from something that already exists. And there is no real easy way to work around that apart from file system deduplication, which is, as far as I'm aware, extremely experimental on every file system that supports it for now. So that's as good as we're going to get with the backups. And what this system does is it keeps the last 30 days worth of backed up roots, and then will automatically purge ones which are older than that. So theoretically, you will have gone and grabbed the data that you accidentally erased by then. And then one final method of retaining your sanity, if backups of your roots is still a little bit too much involved for you, is that you could just half-ass impermanence by mounting your user's home directory on a persistent volume. And this is really honestly the most sane way to do it, because then you get all the benefits of your actual root system having everything declared and defined in it, but then your home user with all of your data and your programs being something that is managed by you. And this is honestly the way that a lot of multi-user systems can ideally operate. This is a way that's a lot easier in terms of not accidentally erasing things that you care about. So just mount home externally. The end. Anybody care? Yeah, you could do, if this is a virtual machine, just have the actual virtual machine not mount some external volume and just create itself on boot, where you then go in and grab the things that you want.
The tricky thing is that usually you don't want to be running like a cow system in a virtual machine on top of a cow system.
Right, and then the other tricky thing would be that you do have to have the boot files. You do have to store everything, which I guess that's not very tricky, but it does. You do have to have a disk. So the actual benefits of doing this in a virtual machine aren't as good as they sound, because you really aren't storing a bunch of extra things just by having that root separately from the data that you're mounting in from outside. Like, just mounting your things in from outside, that is what the impermanence module does, but as an external, just regular mounting storage thing instead of bind mounting to a directory thing. Yes.
I don't know if you covered this, but did you do this on a per user basis? So if you have multiple users, you have one user being non-permanent and then one user being permanent?
You would be able to do that. You would just have to make sure that the /home directory exists before you mark, or actually an easier way to do this would be going through and adding in your impermanent configuration. Let me find the slide. I don't remember exactly where it is. Just mark whichever user's home directory in as part of the environment.persistence.directories table. Just have your user's directory, or whichever users you want to be persisted, marked.
Similar to how the school does their
Oh, you're meaning the inverse, where you're saying only the user's directories are
Yeah,
deleted.
per user,
Uh,
per user base.
So yeah, the way that you would actually do that is instead of mounting root as tempfs, you go through and just mount the users, or even just mount slash home as tempfs, and then you would define through this interface which users you want to actually persist, and the all the users which you aren't marking are going to be deleted.
Okay.
Did you ever try working with TFFS first before you did
I
DTRFS?
did. I am actually the setup that I have on my, all right, the setup that I had on my laptop was tempfs root.
How did that work? Like, did you ever run into memory problems?
I really honestly did not run into memory problems because, as scary as it sounds, putting your entire root on tempfs, there's a lot less data on root than you actually think there is. And the vast majority of it in NixOS is going to be a link to the Nix store. So this is the vast majority of the files that are existing on your tempfs root are just symlinks. So anything larger than that is going to be mostly related to logs, and these text file logs are not going to bloat up your disk unless you spend a very long time without turning off your computer.
Or just like a cache?
Or I did have it set up so that the system would call itself full if 50% of the memory was being used by the tempfs root, but I never got anywhere even close to that amount.
Well, you also mentioned an example, uh, playing Minecraft in the file save. In that case, that means you're putting a lot of data in the TempFS you shouldn't have. That could have been a potential problem for storage, right?
That would have been a potential problem if I had started to run out of space. It only did get to about, like, in that theoretical example, which may or may not have happened, it only took up around a gigabyte and a half, which is enough headroom that most people nowadays, I would say, have a gig and a half of RAM. But I speak from a location where I get to have 32 gigs of RAM, so it really doesn't matter. But tempfs root is something that you really only should consider if you actually have the RAM headroom.
Also, files stored on FFS will be swapped out super easily. Like they'll be first
Yes,
picked.
tempfs does prioritize itself for going into the swap that is on your system if you have any swap.
That's interesting because I know the rest of Linux does not like this stuff. It's like the last thing they ever
Tempfs assumes that the things you're storing on it are files, and so it will put itself into the non-RAM RAM.
There's a swapping this character.
I'm pretty sure it has to do with how the kernel manages different parts of memory rather than the swappiness of the swap file.
Oh, wait, true. The swappiness applies to the swap by itself.
All right, well, that about finishes it.